Yesterday we discussed what are known as discrete distributions. So we said that whenever you are having sort of count data where values are only in integers, then in those situations we use those distributions known as discrete distributions. But many a times we may be recording values which are non-integers also, or they can take values in a certain range. For example, if I record say height of individual or weight of individual, then it could take any values in some interval AB, right? For example, if I am talking about human height, adult human height, then maybe somewhere between say 2 feet to 9 feet, even if I allow for extremes. Then any value in between is possible, correct? It's not just integers 2, 3, 4, or not even like fixed fractions like 2.1, 2.2. Technically, if you have a precise measuring instrument, then any value may be something like 2.1, 5.112, like this would also be a possible value. So in such cases we go for what are known as continuous distributions. Okay, such random variables which take values in some interval are known as continuous random variables, and we go for continuous distribution to study probabilities associated with such random variables. And one of the very important continuous distribution is normal distribution. Okay, we are going to study it in detail because whenever we do any further exercise in statistics like testing of hypothesis or something like that, then we need normal distribution. So normal distribution is characterized by its peculiar shape, which is known as bell shape. Okay, so this is a typical bell shaped curve, and it is symmetric. Now you know what is symmetry, right? Everyone knows what is symmetry. So if I fold this on this vertical line, then the two parts exactly overlap each other. Okay, so in that sense it is symmetric. So it's a symmetric bell shaped curve, and it has lots of applications. Especially in quality control, you might have heard something called as 6 sigma. Have you heard of something called as 6 sigma limits or 6 sigma quality control? No, okay, then forget it. So why normal curve is so widely used? First of all, it represents most of the natural phenomena. For example, if I talk about heights, and let me focus on say only one gender. So for example, if we talk about say heights of adult males, then majority of the people will have like average heights, so heights in maybe some such interval. But then we will also have people on both the extremes, few people who will be very tall, few people who will be very short, etc. And generally the proportion of people who are very tall would be similar to proportion of people who are very short. Same story with weight. Majority of the people will have near average weights, we will have extremes on either sides and roughly equal number of extremes on either side. So most of the natural phenomena seem to exhibit normal distribution, hence it is quite widely used. Okay, there are some more interesting properties of normal distribution, but before that let me introduce notations first. So we say that a random variable x follows, so this symbol is follows normal distribution with mean mu and variance sigma square. So this is mean and this sigma square is called as variance. You know variance, right? You have seen mean and variance, sample mean and sample variance you have computed using exercise, right, using the given data points. So this is known as population mean and population variance. So we say that x follows normal distribution with mean mu and variance sigma square. For example, for height, this mean could be somewhere around maybe 5.3 feet for 5.3 or 5.4 for females, and then maybe something like 5.5 or 5.6 for males, at least in India. Okay, and sigma square gives us idea about the spread. How does it give idea about the spread? So actually, when I say that this is my normal curve, so this spread depends on sigma. So if my sigma is large, okay, if I have some other distribution, other normal distribution with same mean and different sigma, then it could look something like this. Okay, so larger spread. If I have smaller sigma, then it may look, and same mean, then it may look something like this. Okay, so the spread is less. Are you getting what I am saying here? The horizontal spread is some sort of function of sigma. We will see exactly what function later. And the peak is always at the mean mu. The tallest point is always at the point mean mu, and it is symmetric, means for normal distribution this parameter mu is equal to mean. It is also equal to mode. Mode means the highest probability associated with it, so tallest point, and it is also median. So median means it captures 50% of the data. So left side is 50%, this side is 50%. Okay, 50% of the probability is to the left of the peak, 50% of the probability is to the right of the peak. Okay. So normal distribution is symmetric around mean, which is also mode and which is also median. Further, so if I have two different means, then of course the peaks would be different. So this could be one normal, and I could have this as some other normal. So two different means. Okay, but here I am drawing a picture where mean is constant and variances are different. So orange one has highest variance, so more spread. Green one has lowest variance, so less spread, and so on. Okay. Now, when I say it has normal distribution with mean mu and variance sigma square, then I can write PDF, probability density function, as 1 upon sigma root 2 pi e raised to minus half x minus mu whole square upon sigma square. You need not remember this formula. Okay, you are allowed to forget this formula. I wrote just for the sake of writing, means you should know that some such formula exists. If you forget, it's completely alright. Okay, I don't expect you to remember it. If you remember, well and good, but even if you forget, it's fine. So what does this mean? So this is PDF, and that graph actually looks like this. So associated with this normal, there are some more properties. For example, mu minus 3 sigma, in general x can belong to entire real line. So x can take any real value. Okay, any real number. I am writing minus infinity to plus infinity. So any real number is allowed. But we know that practically when I talk about say height or weight cannot be very high. For example, you know, you can't have a person with 100 feet height, right? But this is fine, because even though in general we allow x to take entire range, most of the times x lies between mu minus 3 sigma to mu plus 3 sigma. So probability of x belonging to this interval is actually 0.9927, something like this. Okay, so it's approximately 0.99. So 99% of the times x would be in this interval, mu minus 3 sigma to mu plus 3 sigma. Now I have some homework from you which you can do even from Wikipedia. So you have to find out what is probability of x belonging to mu minus 2 sigma to mu plus 2 sigma. Okay, this you have to find out. So as I said, even Wikipedia might have the answer. and secondly mu minus sigma to mu plus sigma. Okay, these two values you have to find out, and this value also if you can find out to more accuracy. Okay, 2 more digits, I have not written here, but 2 more digits. So the point of this is majority of the values lie between mu minus 3 sigma to mu plus 3 sigma. Okay, so even though the entire range is minus infinity to infinity, it could be used even for those variables like height, weight, where we know that the actual range is going to be finite. Okay, okay so far. Then there is something called as just a minute. Okay. Then there is something called as standard normal random variable. Okay. So what is a standard normal random variable? So we said that x follows normal distribution with mean mu and variance sigma square. We can define z as x minus mu divided by sigma. Okay, we can define z as x minus mu divided by sigma. Now what happens? Mean of z will be 1 by sigma mean of x minus mu. Mu is constant and mean of x is also mu. So as a result, z has mean 0 and variance also 1, because variance of z will be 1 by sigma square variance of x, and variance of x is sigma square. So sigma square gets cancelled and you get z following normal 0 1. So this z is known as, so this is known as standard normal distribution. Okay, this is known as standard normal distribution, and this is also called as z score. Okay, this is also called as z score. Where is this z score used? Suppose I want to compare performance of two students, but they have opted for different subjects. Okay, so one student has opted for say chemistry and another student has opted for environmental science. Okay, chemistry class has suppose 15 students, environmental science class has let's say 10 students. Okay, so I cannot simply compare rank. So even if I assume that okay, like in general the intelligence levels or sincerity levels of students in both the classes are same, I'll assume that. Still I cannot directly compare ranks because there are 10 people here, there are 15 people here, and then suppose there is a test in both the subjects and in chemistry, so I have one student, let me call that student S1. So student S1 has scored 20 marks out of 30 in a chemistry test. Okay, and student S2 has scored let's say 32 marks out of 40 in a environmental science test. And I assuming that the two classes are more or less similar, I want to compare S1 S2. Okay, I want to rank S1 S2. So I want to see if S1 has performed better or S2 has performed better. So what are your suggestions? Do you have any suggestions? My assumption is classes are same, means my assumption is students taking up these classes are more or less same. So chemistry students more or less have similar intelligence and sincerity level as environmental science students. Okay, I don't know anything about the difficulty level of these tests. So I don't know whether chemistry test was more difficult or less difficult than the environmental science test. So how can I compare performance of these two students in two different tests? Any ideas? Yes? Any ideas? No ideas? Okay. So I will tell you with the help of normal distribution, and then you could perhaps tell me if it is equivalent to some other thing that you might already know. Okay. So what I will do is I will check what is the mean score in the chemistry class, okay, in this chemistry test. So suppose average score here in this particular test is say 18, okay, and average score here is say 28, okay. Then I won't stop at average because you know the total is different. So here the person is 2 points above average, here the person is 4 points above average, but that's not directly comparable because totals are different. So then I will get variance of this scores or standard deviation of this scores. So standard deviation of this scores, suppose it turns out to be 2 here, and standard deviation of this scores, suppose it turns out to be 3 here, okay. Then I will compute z score for each of these students. So z score will be score of that student minus mean score divided by standard deviation. So it would be here 30 minus, sorry, average is so 32 is actual score minus 28, that is average, divided by 3, okay. Now see, z1 is what? Z1 is 2 by 2, so z1 is 1, z2 is 4 by 3, so 4 by 3 is 1 point something, right, 1.33. Now I will compare the z scores. So z score of this person is higher, means this person has performed better, okay. I will compare the z scores. So this is actually, so can you think of what this is similar to? Suppose this is normal curve, okay. Suppose this is normal curve. So z1 equal to 1 is somewhere here, z1 equal to 1.33 may be somewhere here, okay. This is a standard normal curve, normal 0 1 PDF. Then for z1 equal to 1, this is the probability of this entire thing, okay, entire thing to the right of this. This is the probability of someone scoring better than this person, okay, the person who got z1 to be 1. This is the probability. Whereas for z1 equal to 1.33, this would be the probability. So 1.33 is here. So this would be the probability of someone scoring better than that person. So the proportion of people who are scoring better than person with score 1.33 is less than the proportion of people who are scoring better than person with z score 1. Can you see in this graph? Is it okay? Am I audible? So that's why we will say that this person has performed better. Now does this look similar to something? Is there any other thing which you already know and is similar? So have you heard of percentiles, percentile ranks or percentiles? This is similar to percentiles, okay. So z score can be used for comparing two different populations. That is the advantage of Z score. That is the advantage of computing Z instead of simply stopping at normal distribution. Okay. And these probabilities are actually available either in software or in tables. So, we can use these probabilities to draw more conclusions. So, what are the chances that a person scores better than 1.33? What are the chances that a person scores better than 1, etc. Okay. And as I said, any normal distribution can be converted to standard normal using this, and we are going to need a few more values from this. So, in this curve, these values are important, 1.645 and 1.96. Why are these important? So, probability of Z being greater than 1.645 is just 5%, okay, so 0.05, and probability of Z being greater than 1.96 is even half of that, so it is 0.025. Okay. So, just remember these two values, 1.645 and 1.96, because we are going to need them a lot when we do when we construct confidence interval or when we do some sort of testing of hypothesis. Okay. Now, let me show you the normal tables, how do they look like and how we are supposed to use.
Yes, ma'am.
So, here, so there are different types of tables. So, I have opened one particular normal table where they are giving this shaded region. Okay. So, for 1.96, the area under this curve in the shaded part is 0.975. I told you beyond 1.96 you have 0.025. So, up to 1.96 you have remaining, that is 0.975. So, how do you compute that? So, let me check 1.96. So, what you have to do? So, in this first column I have to locate 1.96. Okay, this is minus, so I have to go for plus 1.96. So, actually I do not have 96, you can see here I have 506070. So, I locate 1.90 and then I have 0, 1, 2, 3, 4, 5, 6. Okay, so 1.96 is actually value corresponding to this. See, can you see that value here? Let me highlight. Can you see the value here? 0.975. Can you see my cursor? Can you see this value?
Yes.
So, it comes from 1.90 here and then 6 here. So, 1.96, 0.975. So, similarly now I can check for 1, right. We computed 1 and 1.33 as two values. So, for 1 value below the curve is 0.8413. So, 0.8413 means roughly 16% 16, okay, roughly 16% students will have Z score higher than 1, whereas if I go for 1.33 then I have 1.30 here and then 3 here. So, 1.33 means this. So, the value is 0.9082. So, only around 9% students will have Z score higher than 1.33. Okay, so, the person in EVS only 9% students will be ahead of him or her, whereas for the person in chemistry around 16% people will be ahead of him or her. Okay. As a result, we would consider that okay, the student in EVS has performed better because there are only 9% students ahead of him or her. Got it? How do you use Z score along with this table? You can check reverse way also. So, I told you that 1.645, beyond 1.645 only 5% values are there. Okay. So basically we have to locate 0.95 in this table. 0.95 is not there, 0.9495 is there and 0.9505 is there. So in between these two values I have 0.95 and that is corresponding to 1.60, and then here C after 4 but before 5. So that is why I wrote 1.645. Okay, so 0.95 probability corresponds to 1.645. Is it okay? Are you getting what I am saying here? So let me show. So data from National Oceanic and Atmospheric Administration indicate that yearly precipitation in Los Angeles is a normal random variable with mean 12.08 inches and a standard deviation of 3.1 inches. And we have to find probability that the precipitation during the next years will exceed 15 inches. You can see why such guesses are needed. Okay, for example, you want to decide what are the chances of uh, if the rain exceeds 15 inches, then what are the implications of that? How much rise will be there in the river level? Accordingly, we have to manage the other constructions near river side, etc. Okay. So what is given to us is mean is 12.08 inches and standard deviation is 3.1 inches. So we will say X follows normal distribution with mean 12.08 and variance 3.1 square, and what we want to find is probability that the precipitation exceeds 15 inches. So probability of X being greater than 15, and tables for all normal distribution are not available. In the software you can easily get this probability, but if you want to use tables then you have to go for Z score. So Z score of this will be 15 minus this mean value 12.08 divided by the standard deviation 3.1. Okay. So whatever is this value, so this will actually be roughly around 1 because 15 minus 12 will be roughly around 3 and this is again 3.1. So this will be roughly around 1, and probability of Z being greater than 1 we saw is roughly 16%, we saw just now in the table. Okay. So this is how normal distribution can be used for solving such problems, and as I said, generally we convert it to Z score first so that we can use the standard normal tables. Okay, so far? So I will try to send a problem sheet where we would have some numerical problems on discrete distributions as well as this normal distribution Z score part. So tomorrow you have holiday, I guess. So tomorrow, day after tomorrow, you can try to solve those problems. Okay, and then next week we will start with the new topic. Okay.
Yes, sir.
Okay. Let me stop here. Thank you.
Thank you, ma'am.